All right, there we go. All right, so number one says this is the NMR spectrum of compound X. So, deduce which of the following compounds in X and explain your answer. So remember, in the NMR, there are three hydrogen environments. So there's three peaks. So this is propanone. It only has one hydrogen environments. If I look at this compound, which would be propanal, it has 1, 2, 3 hydrogen environments. And this compound here, I'm just thinking about how I would name this thing. I'm not going to try because it's got an alkene and a hydroxyl group, but it has 4 hydrogen environments. So remember, the number of hydrogen environments in the molecule is equal to the number of peaks, which tells us that the compound in the middle, propanal, is our compound. Now, we can also confirm this by looking at the integration traces. I don't know why this is so far out of focus. I guess that's a little better. All right, so the integration trace is this little integral symbol with the number. It tells us how many hydrogens are in each environment. So in this compound, if we look, 3 would be that, 2 would be that, and 1 would be that. All right, so for the explanation, you can do a number of things. You could say that propanal has 3 hydrogen environments, or you could say that the integration trace matches this compound and only that compound. One more thing you could say. Notice we have this peak all the way up here between 9 and 10. If you look in table 27 of the data booklet, you'll see that the hydrogen atom in an aldehyde will usually show up between 9.4 and 10, which tells you the compound is an aldehyde, which is why it's that one. Now, this question here always gives kids a lot of problems. Just know that the reason why peaks show up in the NMR is the way those hydrogens are bonded. So we want to look at hydrogens that are bonded in a similar way in the other two compounds. Now the first thing I see here, first of all, propanone and propanal are structural isomers of each other. They both contain the carbonyl functional group. So here I have methyl hydrogens near the carbonyl. So I would say the CH3 methyl is next to the carbonyl. So because methyl groups will always be around 1, but if it's close to oxygen, it gets pushed out a little bit further. So since we have methyl groups here, they're both close to oxygen, I would say that we'll get a peak in this one in a similar spot for the methyl groups in it. All right. Apart from absorptions due to carbon-carbon and carbon-hydrogen bonds in the infrared, suggests one absorption in wave numbers that would be present in the infrared spectrum. So remember, wave numbers is the unit on our x-axis, so it's just where the absorption is in the spectrum. So we got to think about what we've got. So we know this is propanal. So if I draw out the structure, it looks like this. Now the infrared spectrum only tells us what bonds are present in the molecule. So it will basically tell us what functional groups we have. So there's only a few bonds in here. I got bonds between carbon and carbon, but we're not interested in those. We also have bonds between carbon and hydrogen, but we're not interested in those. So the only other bonds that are in this molecule are carbon double bonded to oxygen, and that's it. So if we look in table 26 for the carbonyl bond, we see it shows up between 1700 and 1750 wave numbers. So I would say it would be 1700 to 1750 wave numbers, which is 7 centimeters minus 1. And then suggest the formulas and the mass to charge values of 2 species that would be detected in the mass spectrum. So for the mass spec, we use table 28. Now I know that this compound contains an ethyl group, it contains a carbonyl, it contains methyl groups. So there's a whole bunch of things you could write down here. We would know that there would be a mass to charge ratio of 15, and that would be for the methyl group. Remember, when you're writing the fragments in the mass spec, you always have to add that plus sign afterwards to show that it's an ion. There's also an ethyl group, so that would show up at the mass to charge of 29. And that would be CH2CH3 plus. Also in the aldehyde, you will have that aldehyde group, which would also show a mass to charge ratio of 29. So any two of those three would be perfect. All right, moving right along. So infrared spec is commonly used, blah, blah, blah. Explain why hydrogen bromide is IR active, whereas bromine is inactive. So hydrogen bromide looks like this. It's a polar molecule. The bromine molecule looks like that. It's a non-polar molecule. In order to be IR active, the molecule must be polar. So HBr can absorb the infrared because it's a polar bond. All right, so the IR spectrum and mass spec and the NMR of an unknown compound X has molecular formulas C5H10O2 are as follows. So there's the infrared, there's the mass spec, which we don't even really need here, but whatever. And here is the NMR. So we see there's only 2 peaks in the NMR. And I've written in the integration traces here, it's 1 to 9. But if the numbers aren't there, you have to actually measure the length of the lines, because this line, it takes 9 of those to equal that, or this is 9 times longer than that, which is where we get that 1 to 9. All right, so it says in the IR, identify the bond responsible for each of the absorptions labeled 1, 2, and 3. So let's go ahead and zoom in on our IR. Okay, so the first thing I see, 1 is pointing right in the middle of that broad absorption, that wide absorption. Notice that number 2 is pointing to the tip of the little one. So first thing I'm going to do is look in table 26 so I can see where these particular absorptions will show up. Now, because there's 2 oxygens in this compound, I know that it's either going to be a carboxylic acid or an ester, because those are the only 2 functional groups that we look at that have 2 oxygen atoms in them. And you won't be given, spectra of things that have, more than 1 functional group on them. So if I look at number 1 on table 26, there's 2 oxygen hydrogen bonds. Now we know it can't be an alcohol because of those 2 oxygens. So that must be the absorption for the OH bond in the carboxylic acid. So we see it shows up between 2,500 and 3,000 wave numbers, and it's strong, which means it comes down far, and it's very broad, which means it's all chunky. So if I look here, let me open up the actual lab. Where are you, actual lab? Did I close it? My lord. Why must they? Oh, wait. Oh, geez. The lab is here on the camera. Sorry, it's been a long day. So I see this absorption. The center of it is right before 3,000, which tells me that absorption 1 is indeed for the OH bond. Now notice here it asks us to identify the bonds. Here it asked us to identify the wave numbers. So just make sure you're given what they ask for. All right. So number 2 then. Now, if this is a carboxylic acid, carboxylic acids all have the same type of bonds in them. So let's just assume that we have ethanoic acid here. I have bonds between carbon and hydrogen. I have bonds between carbon and oxygen double bond. I have carbon-oxygen single bonded and oxygen to hydrogen. We've already identified that one. Now, this absorption here labeled 3 is right there at 1700. You're going to see that one a lot. The one at 1700 is for the carbonyl group. So number 3 is for the C double bond O. Sorry, I can't see it. All right, and finally for number 2, since we've ruled out all those bonds, it could either be the carbon-oxygen or the carbon-hydrogen bond. But if you look in the data booklet, it says that carbon-oxygen bond shows up between 1050 and 1410. So it would be in this range of the period of the spectrum, But 2 is up there, which means it must be the carbon-hydrogen bond. if I look in the data booklet, the bond between carbon and hydrogen, where are you? Where are you? There you are. Will show up between 2850 and 3900. So that one fits the bill. So the number 2 is our carbon hydrogen bond. So this is really kind of about ruling things out. So figure out first what it couldn't be. When you do that, you'll figure out what it must be by process of elimination. All right, here it says, in the mass spec, deduce which fragments have mass to charge values of 102, 57, and 45. So the biggest one that's given to you is usually the molecular ion peak, which is the molar mass of your compound. I'm looking for my calculator here. There we go. There we go. So usually, like I said, that's probably going to be the mass of our compound. Well, we were told that the molecular formula was C5H10O2, so we can actually test that theory out. So C5, so 12 times 5 for the 5 carbons, plus 10 for the 10 hydrogens, plus 32 for the 2 oxygens, gives me 102. So that is indeed the mass to charge of the entire compound. The entire compound is C5H10O2. So what we write up here is C5H10O2, because we're writing it as a fragment in the mass spec, add the plus sign. Now if I look in the data booklet for a mass to charge ratio of 57, what you'll notice is we don't have it. I do have 45 though, and 45 will be the carboxyl group in the carboxylic acid. So we can just write here COOH plus sign for our carboxyl group. Now, this compound, when it goes through the mass spec, it gets broken up into chunks. So if something exists with a mass of 57, that means when this thing broke apart, it produced a fragment with a mass of 57. So all we have to do is subtract 57 from 102 to find out what that fragment was. So when I go ahead and do that, 102 minus 57, I get 45. That means an entire molecule had a carboxyl group break off, leaving behind a fragment with that mass of 57. So all we have to do to find the formula of that fragment is subtract the atoms that were removed from it. So in that carboxyl group, 1 carbon broke off, leaving us with 4 carbons. Both of the oxygens broke off, and 1 of the hydrogens, leaving us with a fragment that would have 4 carbons and 9 hydrogens. Don't forget to add your plus sign. So just like we talked about in the notes, if a fragment is in the data booklet, subtract the mass of that fragment from the molecular ion, and you'll find out what broke off, subtract what broke off to get the fragment that remains. And you can always double check yourself, because the masses of 4 carbons and 9 hydrogens should add up to 57. So we do 12 times 4 plus 9. What do we get? 57. All right, identify the peak at 11.5 parts per million. So we know that this is a carboxylic acid. So when we look in table 27, we're going to look for a type of hydrogen that would show up at that range. Or actually, why even use the data booklet? Because I'm given the NMR. There's the peak at 11 point, what did it say? 11.5. There's only 1 hydrogen in that environment. So it must be the hydrogen on the carboxyl group. So you can just write, it's the hydrogen on the carboxyl group. And you can write out carboxyl group, or just write its formula, that's fine. All right, stay-with information can be obtained from the integration traces. This is just a definition. The integration trace is the number of hydrogens in each environment. So the peak at 1.2 has an integration trace of 9. That means there are 9 hydrogens in it. So you can just write here, there are 9 hydrogens in the molecule. Now, what I told you guys in class, whenever you see that integration trace of 9, generally, in this class, what it always means is a carbon atom that has 3 methyl groups bonded to it. So first of all, those hydrogens would all be in the same environment because they're all bonded to the same carbon atom, and there's 3, 6, 9 of them, so that's usually what it is. So this is a carboxylic acid, so it'll feature our carboxyl group, well, that's got to be bonded to a carbon if that carbon was the one with 3 methyl groups surrounding it. Then this structure would be consistent with the NMR because it has 2 hydrogen environments, 1 hydrogen in one environment, 9 in the other, and we can confirm that the molecular formula would be C5O2H10. Now, if you tried to draw just a straight chain carboxylic acid, what you'd get is a molecule with 1, 2, 3, 4, 5 hydrogen environments, so it can't be that because we would have an NMR with 5 peaks. All right, next, moving right along. All right, so first thing I can tell you, this compound is an ester because I see that COO in the middle of a carbon chain. So this says this is an isomer of compound X. Deduce 2 differences between this NMR and the NMR of X. Well, first of all, this molecule has 1, 2, 3, 4 hydrogen environments. So one difference is that there would be 4 peaks in the NMR of this ester. And one big difference is we would have a different integration trace because it would be 3 to 2 to 2 to 3 as opposed to 1 to 9. So just think about what the HNOMR spectrum gives us, and that'll tell you basically what the differences must be. Because what does it give us? It gives us the number of hydrogen environments, it gives us the integration trace, and it gives us the splitting pattern. So you could say there would be a different splitting pattern, since in this molecule all of those hydrogens would show a singlet because the carbon bordering it has 0 hydrogens, and this one would be a singlet as well because the carbon bordering that also has 0 hydrogens. And if you look at that NMR, you can see they're both singlets. All right, so finally, we're given 4 alcohols: butane 1-ol, butane 2-ol, 2-methyl-propan-1-ol, and 2-methyl-propan-2-ol. So I'm going to go ahead and write the structural formula for each of these. So butane 1-ol looks like this. To save time, I'm going to not draw in the hydrogens, but at the end of each of these bonds is a hydrogen. Here is butane 2-ol. Two-methyl-propan-2-ol. Oh no, I have to go to a meeting. I have to go to a meeting in 12 minutes. I'll try to finish up. All right, so here's 2-methyl-propan-2-ol. I could have just written those as CH3s too. I'm just being lazy. And finally, 2-methyl-propan-1-ol. So prop tells me 3, 1-ol tells me the hydroxyl group is on carbon 1, and I got my 2-methyl here. So here are my 4 structures. Now let's see what they want us to do. Ooh, it describes 2 NMRs. It says details of the NMR of 2 of these alcohols are given below. Spectrum 1 has 2 peaks, and spectrum 2 has 4 peaks. Consider the proton environments present in each one of the alcohol molecules when answering the following questions. Identify the alcohol which gives spectrum 1 and explain your answer by stating which hydrogen atoms in the molecule are responsible for each of the 2 peaks. So if there's 2 peaks in the spectrum, it means it's going to be the alcohol with 2 hydrogen environments. So butane 1-ol has 5 environments. Butane 2-ol has 1, 2, 3, 4, 5 environments. 2-methyl-propan-1-ol only has 1 environment because 2 environments because these methyl groups are equivalent and that hydrogen is in its own. And this one would have 1, 2, 3, 4 environments. So it's got to be 2-methyl-propan-2-ol. So it's 2-methyl-propan-2-ol because that's the only one with 2 environments. So there's only 2 types of hydrogens because there's only 2 environments. Now, we're told that there's 1 peak at 1.3 that has an integration trace of 9, and the other at 2 has an integration trace of 1. So if we look at this molecule, you have 9 hydrogens in one environment and 1 in the other one. So the peak at 1.3, because it has the integration trace of 9, was caused by the methyl hydrogens. And the peak at 2.0 must be the hydroxyl hydrogen because it's got an integration trace of 1. Deduce which alcohol gives spectrum 2. So spectrum 2 has 4 peaks. So I got to choose the alcohol that has 4 environments. That would be 2-methyl propane 1-ol. So I forgot my dash here. 2-methyl propane 1-ol. Wants us to explain which particular hydrogen in the molecule are responsible for the peaks at 0.9 and 3.4. So at 0.9, it's got an integration trace of 6. So in this molecule, this is the environment with 6 hydrogens in it. So at 0.9, it's caused by our methyl hydrogens. The peak at 3.4 has an integration trace of 2. So in this molecule, we have to pick the environment that has 2 hydrogens in it, which would be those methylene hydrogens. So the CH2 gives us the peak at 3.4. Finally, looks like I'm going to make it. Deduce which 2 of the alcohols could produce a spectrum and identify the species responsible for the 3 peaks. So we're told there's 3 peaks in the mass spec, 74, 59, and 45. So all 4 of the alcohols will have the 74 because that is the molecular ion peak. Now, if I look at table 28, I don't see a mass to charge ratio of 59, but if I take that 74 and subtract away that 59, ooh, 15. Well, oh, Jesus, I dropped my data booklet. If I look at table 28, mass of 15 indicates that a methyl group was lost. So our alcohol, if it's going to produce that mass spec, has to have a methyl group. Well, methyl group, methyl group, methyl group, methyl group, they all have methyl groups. So we can't, so they'll all have that peak because they all have that thing. Now for 45, if you look in the data booklet will tell you that it's for the carboxyl group in a carboxylic acid, but that can't be the case here because these are alcohols. So let's go ahead and take that 74 and subtract the 45. Ooh! So something broke off that had a mass of 29. If I look in my data booklet, the mass of 29 corresponds to an ethyl group or the CHO in an aldehyde. Since these are alcohols, it can't be the CHO, which means the alcohols that produced this spectrum must have a methyl group present, or an ethyl group, present in them. So the only 2 alcohols that have ethyl groups in them are butane 1-ol and butane 2-ol. So butane 1-ol and butane 2-ol. Identify the species, deduce which 2 of the alcohols and identify the species responsible for the 3 peaks. So the peak at 74 was the whole thing. So these are all C4H10O. So that's my fragment that made that peak. We already indicated that the fragment that made the peak at 59 was that minus a methyl group. So I just have to subtract 1 carbon and 3 hydrogens from that. So that would be C3H7O. And the thing that made the peak at 45 was our compound after losing an ethyl group. Now an ethyl group is C2H5, so we take what we started with, subtract 2 carbons to get C2, 5 hydrogens to get H5, and then, oh, because that didn't break off. So you can add them up. That should add up to 59, that should add up to 45. So let's see if it does. So 12 times 3 plus 7 plus 16 equals 59. Sweet. And 12 times 2 plus 5 plus 16 equals a 45. Nice. All right, the spectrum also shows a significant peak at mass to charge of 31. So suggest which alcohol is responsible for the spectrum and deduce the species responsible for the peak at 31. So if we take 74 and subtract 31, we get 43. Oh wait, hold on. Oh wait, yeah, hold on a second. 74 minus 31, yeah. Which is 43. I'm gonna pause the video here. Derp. We see that the mass of 31 is caused by the CH3O. So we can write CH3O as our fragment, and it means this thing with a mass of 74 lost that. So one of these two alcohols has to have a contiguous piece that's 3 hydrogens, carbon, and 1 oxygen. So the only one I can see that would fit that bill, CH3O, would be the butan 1-ol. Because here, if I was going to have C3 with the O, I need that H. If that broke off, remember, that's both connected to the carbon. So it has to be a butan 1-ol, a butan 1-ol, and that's the fragment responsible. And finally, explain why I lost my computer. My whole computer